Hello everyone, welcome to our very first topic of ECH 3123 material balance, which is on chemical engineering calculation. This topic covers mostly on units and dimensions, and you will learn the foundation of everything that you will do later in chemical engineering, like process design, thermodynamics, and transport. Understanding units and dimensions looks very simple, but it is one of the most important skills that you have to master before being a professional engineer. At the end of this topic, you should be able to identify common units and carry out unit conversion using conversion factors and also solve engineering problems that require unit conversion. So the subtopics of this chapter includes units and dimension, conversion and system of units, and force and weight. Before we start, let's start with a simple question. So why do we even bother to learn about units? Because actually units aren't just labels, they give meanings to number. For example, if you write a number 5, it doesn't mean anything unless you put a unit next to it. For example, 5 kilograms or 5 liters. So that 5 value can mean anything if you don't put the unit next to it. So engineers rely on precise communication, so a tiny mistake in units can lead to huge consequences. And one of the consequences that already happened is on a spacecraft of NASA. Let's watch this video.
I'm Dr. Matt Schindel. I'm a curator here at the National Air and Space Museum, where I curate our collections related to Earth and planetary science. So after the end of the first era of robotic exploration of Mars ended in the 1970s, it took about 20 years before the US started sending spacecraft to Mars again. And so in the 1990s, you started to see US missions to Mars again. And there were a couple of missions sent during that time that unfortunately had poor ends. And one Mars spacecraft that had a particularly bad end was the Mars Climate Orbiter, which the US launched in 1998 on the way to Mars. And when it got to Mars and when everyone was ready to celebrate the fact that it was going into orbit, suddenly NASA lost communications with it. And what turned out had happened was that the software on the spacecraft had a different software from the software that was being used at Mission Control, one of which used metric units and the other used English units, or feet and inches. And those two software were supposed to be able to communicate with each other, but because the numbers from one weren't being converted into the units of the other, the spacecraft either ended up burning up in the Martian atmosphere or speeding off out of orbit of Mars and ending up in an orbit around the sun. We don't actually know what happened to it, but we know that we didn't get the years of data that scientists were hoping to get from the Mars Climate Orbiter because we lost it. So this is why when we write down our measurements, it's important to actually indicate what units we're using. Otherwise, you could be communicating something very different from what you think.
So this is a very famous example of a disaster that is caused by merely wrong unit conversion. So in 1999 or 1998, NASA lost a $120 million spacecraft, the Mars Climate Orbiter, because there are two engineering teams doing the project, one doing on the calculation on the thruster, and another engineering team do calculation on the mission control. So both the two engineering team use different unit system. The spacecraft thruster use Imperial British unit, whereby the units are in pounds and in pound second. But the NASA navigation team at Mission Control is expecting metric unit, which is in Newton second. So that mismatch caused the thruster unable to enter Mars atmosphere. So it enters at the wrong angle and finally burn. So that is a very small unit conversion error, but one big disaster. So from this experience, we learned that we have to always treat units as part of the numbers, not as a label or just a decoration, because the units give the numbers a value, because each unit also has its own value. Okay. Now, let's continue. Okay, this is the first subtopic of our chapter, which is unit and dimension. You have to understand what each means. So each quantity here has a numerical value and a unit. For example, 2 meters, 4.2 kilograms, 5.6 hours. All of these are quantities, and each quantity has a numerical value and also a unit. A unit is placed next to the numbers, and it means something. When you already put the unit, you know that it is a dimension. So a dimension is a property that can be measured. So each quantity here has its own dimension. If we put meters next to a number, we already know that it is a dimension of length. If it's in kilogram, and then we know that it is a dimension of mass. Dimension is also categorized into two, which are basic dimensions and derived dimensions. Basic dimensions is like the building blocks of dimension, whereby the derived dimension is obtained by multiplying or dividing the basic dimension. For example, density is a dimension derived from mass and volume. Mass flow rate comes from mass and time, and velocity comes from length and time. So I hope you are clear that dimension is a property that can be measured, and each quantity has a value and a unit. Okay, next up, rule of thumb for units. As a future engineer, you have to always remember to write your units after you do calculation, especially at the final answer, because all the numbers that you write doesn't mean anything if you don't write the units. People will not know what is the dimension of your value. And then, secondly, you have to treat units as symbols that can multiply, divide, and cancel. I believe you are familiar with symbols in maths, such as X, Y, T, and S. All the symbols, you already familiar to multiply, divide, and cancel out. So treat units similar to the symbols that you already learned before. So, for example, 10m over 2s is equal to 5m over s. So m, minute, and s, second, you treat it as symbols. So it doesn't disappear in any parts of the equation. Number 3, lastly, quantities may only be added or subtracted if the units are the same. For example, you can do this 3 centimeter minus 1 centimeter equal to 2 centimeter. But what if the units are not the same? This is where unit conversion comes in, whereby you have to change the units first. So when all the units are the same, then you can do addition or subtraction. We'll cover unit conversion in the next subtopic. Okay, now let's move to unit conversion. As you can see, both of these cars are moving the same speed, but the first car's speedometer shows 180 and the second speedometer shows 111.85. Even though the values looks very different, but the cars are actually moving at the same speed. The difference here is just the unit of the difference is the expression of the speed in terms of kilometer per hour and miles per hour. So 180 kilometer per hour is also same as 111 miles per hour, 50 meter per second, and 1.58 times 10 to the power of 11 centimeter per year. Even though these values are very different, but it shows this it is the same velocity expressed in different units. So how to convert one unit to another? We use conversion factor. It is like a translator between units. Conversion factor is a ratio of two equivalent quantities expressed in different units, which numerically equals to 1. Okay, we will make our own conversion factor from the information that we already know. So for example, we know that 1 centimeter is equal to 10 millimeter. So we convert this information into ratio by dividing both sides with 10 millimeter, and the right side here will equals to 1 because it's the same thing, same value and same units. So when this part is equal to 1, we declare this as a valid conversion factor for centimeter and millimeter. So this one is a valid conversion factor, and the inverse conversion factor is also valid as long as it both equals to 1. Okay. These are the information that is given to you in your textbook. We call this a unit conversion table. The listed quantities here are mass, length, volume, density, force, pressure, energy, and power. And all of the equivalent values are listed here. Okay, so you can refer this table during test and exam. But of course, this table is not complete. Sometimes you have to find the information on your own. Okay, now let's learn about systems of units. There are 4 systems of units that are widely used, which are SI, System International Units, CGS, Centimeter Gram Second, US Customary, and British Imperial System. So SI and CGS system uses metric, whereby the numbers are decimal base, which is multiples of 10, and then US Customary and British Imperial System are non-metric, whereby they use foot, pound mass, and second. So metric SI system is used worldwide in engineering, science, and industry. CGS is mostly used in physics and older scientific work, and US is used in US industries, and British Imperial is historically used in the UK, but now it is partly replaced by SI unit. Now the key characteristics of each system. For SI, it is decimal based, it is easy to convert, and it is standardized globally. CGS is similar to SI, but the scale is slightly smaller, such as for meter. Instead of meter, it uses centimeter. Instead of kilogram, it uses gram. For US Customary, the key characteristic is it is not decimal based. The conversion requires extra constant. For example, if you look at this table at the bottom, the conversion unit use very random numbers. For example, 1 feet equal to 12 inches, 1 yard equal to 3 feet, and 1 mile is equal to 5,280 feet. So this is the meaning of conversions require extra constants, But in metric units, all the conversion are decimal base. It is multiplies of 10. For example, 1 meter is equal to 100 centimeter. 1 kilometer is equal to 1000 meter. British system is very similar to US customary, but there is slight difference in terms of volume and weight. So among all systems of unit, SI unit is preferred by engineers around the world. Why? Because it is very simple, whereby all the numbers are decimal base. It's coherent. Every prefixes are changed to the power of 10, making conversion very simple and precise. We don't need to memorize all the weird numbers such as 1 feet equal to 12 inches. So imagine if you want to design a factory or a chemical process plant whereby you include many international engineers. So we will use SI as our standard unit of system so that everyone is on the same page. Okay. Now, we already know that SI unit is the standardized unit for engineers. So now let's go to prefixes. Prefixes are used in SI unit to indicate power of 10. I think you're already familiar with this tera, giga, mega, kilo, centi, milli, and micro and nano. So all of this information is also included in your book. You don't have to memorize, but you should know how to to use this to convert all your values into SI prefixes in order to simplify your number. Okay, now let's learn about the types of units. There are 3 types of unit: base units, multiple units, and derived units. Base units is the fundamental building blocks of units. For example, meter, kilogram, second, Kelvin, and mole, whereby the derived units are built by multiplying or dividing base units such as meter cube, meter square, Newton, joule, and Pascal. So the base unit for SI unit here are only 5: meter, kilogram, second, Kelvin, and mole. And the other thing that you know, the other units are all derived units that comes from these 5 base units. And then multiple units are just convenient version of base unit. For example, instead of writing 608,000 seconds, it is easier to say 3 years. Or instead of 0.001 meter, we say 1 millimeter. So it is for convenience or to simplify the value that we want to convey. The units doesn't change anything, they just make our life simpler. Okay, another thing that I want you to take note is that for base unit, it always comes from the basic dimension. Remember in the previous slides, I mentioned about base unit and derived base dimension and derived dimension. So the base unit comes from the base dimension and derived units comes from derived dimension. Okay, next is the comparisons of units across 4 systems. We have learned 4 systems just now: SI, CGS, US, and British Imperial. So if you see here, for SI and CGS, it uses decimal systems, whereby in US and British, they use feet and pound system. And I think the most important thing for you to take note here is that for the volume for US and British, even though both says gallon, it is actually a different thing. For US, it's US gallon, and for British, it's imperial gallon. Okay, now let's learn how to do unit conversion like an engineer. So the first task is very simple. Convert 33 milligram to gram. So the first step to do conversion is to find a suitable conversion factor. You can use the conversion table that is provided, but sometimes the information is not there. So you have to use the knowledge that you already know. For example, for now you have to use this, which is 1 gram equal to 1000 milligram, and then you convert that to conversion factor. After you already get your conversion factor, you have to multiply the given quantity, which is 35 milligram, with the appropriate conversion factor. And please use this method from now on. The method that I'm referring to is this method, whereby you are using lines, vertical line to show multiplication, and a horizontal line to show division. So this method is used for unit conversion, especially for material balance subject. Please use this from now on because it really simplifies your calculation step and it reduces the possibility of doing some silly mistakes. Okay, and how to do the unit conversion? You have to just place the given quantity here at the first part, 36 milligram, and then at the next part, you just have to write down the conversion factor that is appropriate. So how to determine between the first one and the second one, which one is appropriate, is you have to make sure that the unit can be cancelled out through division. So milligram is the one that you want to cancel out and you want to remain gram. So 1000 milligram should be at the denominator, 1 gram should be at the numerator. So this, if you calculate it, 36 divided by 1000, you should get 0.036. And the unit that you will get after cancellation of milligram is gram. So this is the final answer of the conversion. Okay, this is the classic mistake that students usually do when they do conversion, because in conversion factor can exist in original form and an inverse form. If you do it correctly, you will get 0.036 gram, but if you misplace the conversion factor like this, whereby 1000 milligram is at the numerator and 1 gram at the denominator, the milligram actually becomes milligram square and the gram will be at the denominator and the value will be very different, which is 36 thousandths. So this is wrong. Make sure that when you place the conversion factor, you can cancel out the original unit and you get a new unit. Let's convert the second quantity, to which is 1 centimeter per second square to centimeter per minute square. So if you see here, we have to convert second square to minute square, which is a squared unit. First step is to find a suitable conversion factor based on information that we know. We know that 60 seconds is equal to 1 minute. So since that the unit is squared, we have to square both sides of the equation here. So this one will be 3600 square and 1 minute square. And then only this part can be used as a conversion factor. So your conversion factor is here. So after you get the conversion factor, again you have to multiply with the given quantity. So 1 centimeter per second square, you multiply with the conversion factor, which is 3600 seconds square over 1 minute square. The second cancels out and you are left with centimeter per minute square, and the value is 3600. The second common mistake that students usually do, especially when involve square or cubic units, they forget to square the values when the unit is squared. So the conversion factor that is correct after you square the values is 3600. When you forgot to square or when to forget to square the value remains 60, and this is a totally wrong conversion factor. When you use the wrong conversion factor, the value will also be wrong. Instead of 3600 centimeter per minute square, you will get 60 centimeter per minute square. Please try to remember, if the unit is squared or cubic, you have to square or cube the values as well in the conversion factor. Now let's do the first example. You can pause this video and try to do it on your own if you want to try. So the question asks you to convert an acceleration of 1 centimeter per second square to kilometer per year square. If you see here, actually we have to do conversion of two different units, which are centimeter and second. Centimeter you have to change to kilometer, and second square you have to change to year square. So use the same method, the vertical line method, as we did in the previous slide, and you have to do one unit first and then continue to the other unit conversion. So the first unit, you can target to change centimeter to kilometer first. So use the conversion factor. We know that 100 centimeter is equal to 1 meter. So this is our first conversion factor, but we are not done because we have to convert that to kilometer. So you have to use a second conversion factor, which is 1 kilometer over 1000 meter. If you are already experienced doing unit conversion, this is actually can be combined into one conversion factor. But if you are just starting to do unit conversion, please do it separately so that you don't do any silly mistake in converting units. And then after you are done with the first unit, you can continue directly with the second unit, which is second square. You want to convert to year square. To convert to year, you have to use 4 different conversion factors. The first one is from second to minute, and then minute to hour, hour to day, and day to year. If you look clearly, all the values here are also squared. 60 square, 60 square, 24 square, and 365 square. When the unit is squared, all the values are also squared. And then when you do calculation for this, you should get 9.95 times 10 to the power of 9 kilometer per year square. This is the second example where it involves imperial unit. So convert 23 pound mass feet per meter square to its equivalent in kilogram centimeter per second square. In this case, you have to do conversion for 3 different units: pound, feet, and minutes into kilogram, centimeter, and second square. You can use the information given in the conversion table. So the first conversion factor to use is the 0.453593 kilogram over 1 pound. And the second one is 100 over 3.2808. For the second conversion factor, is already a simplified conversion factor. It actually comes from 100 centimeter over 1 meter, and the second conversion factor is 1 meter over 3.2808. But since it's the same thing, so I just combine it into one conversion factor into this to simplify my calculation step. And then the last one is minute to second square. Remember, 60 also need to be squared. So when you calculate this, you should get 0.088 kilogram centimeter per second square. Now let's go to the third and last subtopic, which is force and weight. So why out of the sudden we talk about force? Because force appears everywhere in chemical engineering. It appears in pressure concept, work, and also power. Pressure is P equal to F over A. It means force distributed over an area. For work, it is force applied through a distance, and power is rate of doing work. So since all of these are derived from force, it is important for us to learn the units of force. What actually is force? According to Newton's second law, the force is equal to mass times acceleration, meaning force is the effect that causes a mass to accelerate. So according to the system that we already learned, SI, CGS, US, and British, all system has a different units of force, which for SI it's Newton, for CGS it's Dyne, and for US and British, the unit is pound force, and the symbol is lbf. And the definition or the base units of the unit of force for each systems are also different. 1 Newton is equal to 1 kilogram meter per second square, 1 Dyne is equal to 1 gram centimeter per second square, and 1 pound force is equal to 32.174 pound mass times feet over s squared. So this means that 1 Newton is not equal to 1 Dyne and is not equal to 1 pound force. All of these, the values of each unit of force for different systems are different. Please make sure you don't do any mistake assuming that all the unit of forces for all system of units are the same. The symbol GC is sometimes used to denote conversion factors from base unit to derived unit of force. So GC is equal to 1 kilogram meter per second square over 1 Newton. This one represents SI unit, and it is also equal to 32.174 pound mass feet per second square over 1 pound feet. This represents US and British unit. Let's continue with the second part of the last subtopic, which is weight. Why we talk about weight? Because weight is simply a specific kind of force, and we use this a lot when we do material balance, because sometimes the given unit is in terms of weight and we have to find the mass. So weight is the gravitational force acting on mass. The equation is W equal to mg, whereby m is the mass of the object and g is acceleration due to gravity. So mass is constant everywhere, but weight changes with location. I think you're familiar with g value, which is 9.8066, but that is the gravitational acceleration value for SI unit. For CGS and US and British unit use different values, which are 980 for CGS and 32 from 0.174 for US and British units. And all the units are also different for different systems. Okay, that is all for the last subtopic. So now we continue with tutorial. I have provided five tutorial questions. I will show the solutions for question 1 and question 2, and then you try to do question 3, 4, and 5 on your own, and then we discuss later during tutorial class. Okay, the first question is on hydrogen fuel for a chemical plant backup generator. A small chemical plant requires 120 kilowatt-hour of energy per day. The plant manager is considering storing compressed hydrogen gas as alternative to diesel. The energy content of hydrogen is 286 kilojoule per mole, and the molar mass of hydrogen is 2.016 gram per mole. A. Convert the daily energy requirement from kilowatt hour to kilojoule. So the first question, 1A is very simple. We just have to use conversion factor that we can obtain from the table. So 120 kilowatt hour, use this value to convert to joule first, and then use another conversion factor to convert joule to kilojoule, and you should get this answer. Or B, determine the number of moles of hydrogen required per day. For all engineering problems, you have to think the logical answer, the logical way on how to obtain the answer. Most of the time, the formulas are not given, but logically thinking, if you are given the total energy, which is 120 kilowatt, and also the energy content, which is kilojoule, in the unit is kilojoule per mole. If you divide the total energy, the value that you obtain in A, in kilojoule, and you divide it with energy content, the unit of kilojoule cancel out, and the remaining unit is in terms of mole. That's why in order to get the number of moles, we use total energy divided by energy content. So when you divide the values, you should get 1510 moles of hydrogen gas. Okay, C. Calculate the mass of required hydrogen per day. So if you know what is the number of moles, you know the molar mass is given, of course you can find the mass. Mass is equal to number of moles times with molar mass, or logically, if you multiply mole with the unit of molar mass, which is gram per mole, the mole unit cancels out and you are left with gram. And then remember, the question asks the answer in kilogram. You have to convert the answer to kilogram. Next, question 2. Fuel delivery to a remote plant. A mobile pump delivers fuel oil at a rate of 50 cubic feet per meter into a storage tank. The pump runs for 30 minutes during a scheduled delivery. Given the density of the fuel oil is 850 kg per meter cube. A. Calculate the total volume delivered during the 30-minute run in imperial gallons. Okay, so for tutorial number 2, question 2 here, it involves a mixture of metric and imperial unit. So please make sure you do conversion correctly. For A, in order for you to convert to gallon, it is just a simple conversion unit, but the given value is in flow rate, and the question asks you to find the volume. You know what is the volumetric flow rate. The time is given, so logically, in order to get the volume, you just have to multiply the flow rate with the time of the run, which is 30 minutes. So the minute unit cancels out, you are left with cubic feet. And then after you get the value in cubic feet, you just have to use conversion factor in order to convert that into imperial gallon. So the answer is 9,000 imperial gallon. B. Calculate the mass of fuel delivered in kilograms. To answer B, instead of multiplying with the density first, you have to change the unit to meter cube first, because the given density is in metric unit. So to be safe, you just you do conversion first and then multiply that value to the density, and you should get 36,000 kilogram. C is like an open-ended question whereby you have to think. Any answer is accepted, but it has to be logic. So this is tutorial question number 3. You can pause this video to read and do it on your own. This is question 4, pumping crude oil through a vertical pipe. And then last one is question number 5. It is on compressed gas cylinder in a lab. In this one also, involves mixture of metric and imperial units. That is all for topic number 1. Please scan this QR code and spend a few minutes to answer a non-graded quiz, and this also will be your attendance, showing that you already completed watching the video. Please do your tutorial, try redo all the examples and exercise questions that I've provided in the lecture notes. The tutorial question, we will discuss it during a different tutorial sessions, face-to-face class. In the next topic, we will still continue topics on chemical engineering calculation, but that is more on dimensional, homogeneity, significant figures, and dimensionless quantities. So that is all. Thank you for watching. If you have any question, you can directly ask in the WhatsApp group. Okay, see you in the next class. Bye-bye.